OK?
OK.
Mesdames et messieurs, bonjour. Ladies and gentlemen, good morning. I would like first thank you to be here with us in the workshop animated by Sopra Steria company and in particular the subsidiary CS Group. I'm Olivier Alquier, CTO and pre-sales director, expert in data and AI strategy, and I'm here with my colleague Thierry. Thierry, I'll let you introduce yourself.
Yeah. Good morning, everyone. I'm Thierry Péan. I'm in charge of R&D in digital simulation for CS Group. And I will talk to you about quantum computing.
Thank you. So today we are going to speak about artificial intelligence and AI and quantum to help numerical simulations. And we propose you the following agenda. First, a quick overview of numerical simulation in the nuclear field and its current challenges. Next, I will show you how AI can help simulation in these challenges. And finally, I'll let Thierry give you the future view of these challenges through the quantum technologies. So let's start with the first part, numerical simulation challenges. So for several decades, numerical simulation, it's a fundamental pillar of the nuclear field. It helps engineers to model complex physical phenomena such as neutronic, thermohydraulics, structural mechanics, and radiation protection. It allows also reduce the number of costly physical tests, but also justify technical choices to regulatory authorities such as the ASNR. You can see on this slide a timeline with several technical steps of the numerical simulation applied in the nuclear field. Started in 1970 with the Atomic Engineering Code. Today we have several other recognized calculation codes like Apollo for neutronic, Tripoli, Kata for thermohydraulic, Aztec for severe accident simulation, Drakkar for fuel simulation, and so on. The aim of the numerical simulation is to build model more and more accurate compared to the real life. And the current challenge of this topic is to simulate interaction between neutronic, thermohydraulics, and mechanics. And to do this, we need to couple multiphysics and multiscale. And to do this also, we need model with more complexity. And with the complexity, you have also the impact in terms of computing power. You know, that's why the challenges we have is increase the performance on models while reducing their costs, but also while reducing their carbon impact, because it's definitively an important subject and numerical simulation has responsibility on it. Okay? Of course, we have to do this by qualifying more complex models regarding the regulation requirements. Do this also with a decreasing number of experts in nuclear simulations, and of course ensuring digital sovereignty and cyber security. Okay? So to meet these challenges, we have currently some techniques: model optimization, high performance computing, GPU, cloud computing, encryption, artificial intelligence, quantum computing. Today, we are going to focus on two of these techniques, AI and quantum computing. So let's start with the second part, AI for faster models. Before to go deeper into our results in this topic, it seems important to highlight that it's a challenge to integrate AI into CFD activity. And to success, it's mandatory to have a strong collaboration between experts in AI and expert in numerical simulation. That's why CS Group, we are relevant on this activity because we have both experiences for a long time. So we provide data and AI offer over 20 years. We support our customer to create value from their data, from data collection, data organization, data preparation, data science, AI, proof of value, industrialization of proof of concept, and deployment of AI into operational operation to create concrete value. And we have, in the other hand, a long-term, strong offer in terms of numerical simulation for 30 years, and we provide numerical studies, computational science, and we have our own product called ProLB to perform a simulation based on a specific algorithm. Again, before to go deeper in detail in our results, it's important to give you some basics about model. What's a classic physical model and what's an AI model? So a classic physical model is a model taking as an input hypothesis, physical equation, and the expert in numerical simulation designs the model manually with physical value, physical argument. So this model is comprehensive, but sometimes very huge in terms of size and in terms of computer power. In the other hand, AI model is something different. Instead of hypothesis as physical equation, you have data, data set, mathematics, and AI. And the model is not designed manually, but with a training phase, automatically the AI builds the model, and human, the expert, tunes the model and validates the model. And at the end, you have also a model, but not a physical model, but an AI model, a mathematic model, you can see on the right, with not physical variable, but mathematic variable. This model allows to perform simulation, but we have some limit in terms of model because it's less comprehensive, because less physical. It's also less accuracy because the accuracy of the AI model is directly linked to the value, the element we have in your data set. So in this case, we want to reduce the physical model with the AI. So the data set is the simulation performed with the physical model. In this use case, the AI model will have less accuracy than the physical model. Okay? That's why this kind of model, reduced, cannot be applied to all use cases. The use cases interesting for this is the use cases where the speed of the simulation is higher in terms of value than the accuracy. For example, you are in a design phase of a product and you want to test a design quickly, have a first view of your concept. In this case, you can use a reduced model by AI to have quick loop during design phase. Another use case, you are in a crisis situation and you want to have a quick simulation to take decision. You cannot wait 2 hours, 3 hours, a result of a physical simulation. You want a simulation, a value quickly to take decision. In this use case, this kind of model can be a help. Okay? So we work on this topic for 2 years now. We have several references. I can propose you an AI model, reduced model, to simulate dispersion of radioactive waste. I can propose you also AI reduced model for quick assessment in aerodynamic performances. We worked also on a surrogate model with AI to predict deformation in automotive sectors, and we are working currently on an R&D project to simulate a critical nuclear accident with this kind of technologies. So we don't have the time to pass all the subject, or I'm going to focus only on both of them. The first project, the first reference, so you see a car, a crash, and we have currently a physical model to modelize the bumper in blue, the deformation, a 3D deformation of the bumper. So the objective of the project started last year is to train an AI model based on the simulation performed with this simulator and compare result performances between the physical model and the AI model. So the result is here. So you can see at the center of the slide a 2D view of the simulation, taking account that it's a 3D modelization. It's just for the presentation. So you have in red, in green, sorry, the result of the physical model, and in brown, the results of the AI model. So visually, we can see that the accuracy, it's really interesting, except in certain area. After measurement, we can say that the AI model in the 3 axes has approximately 90% of accuracy compared to the physical model. I give you also some duration element to train this AI model. It costs 1.5 hours time with a big infrastructure, because we are saying 2 NVIDIA H100 GPU, so it's not a classic computer. And this is interesting. Once the model trained by AI, the execution of the simulation takes only 1 minute. If we compare to the time for the classic physical model to execute the same simulation, we see that in our use case, the AI model is 60 times faster than the physical model, with an interesting accuracy. Another use case to go deeper into nuclear activity is the ASAS project. It's an European R&D project, artificial intelligence for simulation of severe accidents, start 2 years ago. The objective of this project is to create a simulator to take decision if in the future we have a severe accident, okay? And we have several challenges, creation of data set, because it's a chance for all of us. We don't have data coming from a real accident, severe accident, so create the data set, create the physical equation also to do the physical, to perform the physical model. And currently we have in the phase where we are training an AI model, and we are looping between the physical model, the data set, and the training of the AI model to reach sufficient accuracy for this use case. But it's just an example to show you that this technology, AI model, is of course also an interesting lever in the nuclear sector. So the last slide to terminate this part is just to give you a summary about all the elements I push you. So first, yes, it's possible to accelerate simulation with AI model based on a physical model. Yes, this AI reduced model can achieve interesting accuracy, but keep in mind that it's interesting for certain use cases. Again, an highlight, this activity, the training of AI, require important computing resources. Okay? And the last point, before to give the ball to Thierry, we also observe an expected added value of this kind of project is a win-win loop between CFD experts and AI experts. Yes, we see in our slides that the experts of CFD provide information to build the AI model. But we observe also that the mathematical approach, statistic approach of the AI experts gives input to CFD experts to optimize their physical model. We observe clearly a valuable loop between these two kinds of expertise by treating this topic. So now, I'll let the ball to Thierry for the last part, quantum breakthrough performance.
Okay, thank you, Olivier. So now I will talk to you about quantum computing, and we can use it eventually in the nuclear industry. So firstly, we'll have some basics on quantum computing. First of all, France is really good in quantum computing, especially in quantum physics. Alain Aspect and Michel Devereux already won 2 Nobel Prizes and for their work in the 80s. And so this translates into very dynamic quantum ecosystem in France right now. And we have some worldly known startups like Alice and Bob and Candela that really leading the way in quantum computing. So regarding quantum computing, yes. In classical computing, we use bits. Can be either 0 or 1. But when we switch to quantum computing, you have to consider like a statistical approach, and we use qubits that can be either both 0 or 1. It can be 80% 1, 20% 0. And this is possible because of two main quantum phenomena. The first one is superposition, because qubits can, when they are in this quantum state, they can be both 1 and 0. Like this, for example, when you consider classical computing, if you think of, for example, of a labyrinth, for the input to the exit, entrance to the exit, you can code only one way at a time. But if you take advantage to quantum computing, superposition and entanglement, finally you can simulate 2 power n permutation for quantum computing. For example, in classical computing, if you want to solve a labyrinth, for example, you can do it only one at a time, but if you have enough qubits, you can explore all the ways at one go. For example, if you have 45 qubits, which means 35,000 billions of combinations. So this translates in digital simulation the ability to have many calculations at the same time. We can translate in improved accuracy, quantum speed up, and also reduce usage. For example, in digital simulations, that means also we can say that standard simulation with million cells mesh can switch to billion cells mesh, which is very convenient to evaluate very tiny phenomena that we should not take into account before. But to do that, you need to take your use case, your phenomena, your problem you want to solve, to formulate it in a quantum circuit. And this is a new way of thinking. So you can say in the sketch, each line represents a qubit, and each box you see on the line represents a mathematical operation you did on a qubit. And we take advantage of this new kind of physics, new kind of way of handle problems to use superposition and entanglement to maximize, to make a maximum operation at the same time. So right now, we are very in the beginning of quantum computing. Unlike classical computing, we don't have a lot of algorithms that we can use. So each time we make a new quantum project, we have to develop new quantum algorithm and somehow also adapt to the new problem. So as of now, we don't know if we can handle all the problems, but at least we know we can do something like factoring large numbers, cryptography, also all optimization problems, and also some digital simulation, like example in nuclear industry. But there are still some limitations. Right now, the hardware in quantum computing is not what we need. The computers are very noisy. We have limited number of qubits. We have a lot of noise, and we have also very limited decoherence time. Decoherence time is the time when your medium, it could be supraconductor, it could be photon, it could be electrons, atoms, when the particle is in quantum state, which means you can use superposition and entanglement. And this, to do a lot of calculation, you need a bigger decoherence time. So, but right now we are in the phase of making proof of concept while performing project. And for that, we can use very useful tools like quantum emulators, which actually use a classical computer, but emulate the behavior of quantum computers. So we can do a lot of qubits with these new tools, but for example, NVIDIA break the record with 45 qubits emulated on one of their machines. So we can emulate easily like 10 qubits, even 20 qubits using these quantum emulators, which can allow us to verify if our quantum algorithms are good or not, because there's no noise when you use quantum emulators and you have no problem regarding decoherence time. You can verify a lot of tests with quantum emulators. And this way to use quantum emulators means we are making a gamble on the noiseless quantum computers that will come in the years to come. For example, IBM said they should be able to deliver 200 qubit FTQC, which means a noiseless quantum computer, by 2030. So it's 5 years down the road. So here you can see our references in quantum computing. The first one was to analyze Earth observation images and to sort out these images according to the area of interest. We also use quantum algorithm to model SO2 molecules. It was to analyze for emission forecastness in which state SO2 molecules was on atmosphere in exoplanets. And we will focus now on the last two references. The first one on Lattice-Boltzmann, more R&D project, and also trajectory optimization for a rocket. So this one is really a PhD that started last year. And as I told you, we are not very good on our quantum algorithms. So in this thesis, we want to develop algorithms that can allow us to solve partial differential equation that is used in the Lattice-Boltzmann method. Lattice-Boltzmann method is a method we use for our CFD software SPRLB. You can check the QR code to see our software. And the goal, ultimate goal for this PhD work is to have some algorithm to use to add another quantum module to ProLB software. So this is, let's say, a few years down the road. And then for this, CNES wanted to know if it was possible to use quantum algorithm, because for them, if you can calculate a better trajectory for rockets, that means you will use less fuel and you will have more payload, which will allow CNES to have more money. So in this project, we use quantum algorithm. We add some hurdles because the state of art is very limited in this kind of science. And we use a trick, I will show you. To solve this problem, we use an hybrid quantum classical algorithm, because you need to know in quantum computing, you don't have random access memory. So you don't have access to, let's say, intermediate values. So you have the beginning and you have the end. And you have nothing in between. So sometimes you need to save intermediate values, you need to, like we did, to stop your quantum computing project and then switch to classical computing, save the value, and go back to quantum algorithm. So we use this trick for this project. For example, we use 5 qubits and less than 1,000 gates. And so, in summary, sales group, we believe in quantum computing. We started to really work on it on 2021. We have, as I said, a PhD working on R&D work right now. We're also part of Sopra Steria network. We also have some references in quantum computing, especially on optimization problem. They did it on Telefonica in Germany for communication networks, and also on logistics for SNCF in France. And also, they are very involved in the quantum ecosystem. They are partnership with Alice and Bob, Candela also, and they also have investment in the coordination funds, which means they have somehow some links with other startups like Pascal, C12, Cobley, and so on. So this is very quick, but this is the end on quantum computing, just on time.
Thank you very much.